So, basically, in the last lecture, we went over some of the properties of quantum mechanics. And I'll just note them here down quickly. The first thing that we have learned is that quantum mechanics is a probabilistic theory. The second thing that we learned is that basically all that we can know about the system is contained in the wave function. That we sometimes call it probability amplitude. We learned that if we want to know something about the physics of the system, we have to define an operator which corresponds to some tangible, measurable physical quantity. And we have learned how to obtain averages of this quantity through using the wave function and more generally not only the average, but also the average of any moment. So it could be to power n, and we know how to calculate any average of any moment of an operator. We gave also a dictionary of some particular operators like momentum and position, and basically in a nutshell that's all we did last lecture. Okay, what I want to do in this lecture, actually three things. One is to look a bit more into these properties. We will see that we started in the last lecture seeing that all kinds of relations that we are familiar with from classical physics are also fulfilled for the average of these quantities in quantum mechanics. Specifically, we will look into the Ehrenfest what's it called? Theorem, although it's a big name for something that's a direct calculation. Then we will see something interesting that happens in a case where the potential does not depend on time. You'll see that we get some very interesting results regarding the energy operator in that case. And the third part, we will do a hopefully, very fast crash course in linear algebra for the simple reason that all of quantum mechanics is linear algebra. So it's good that we will be well versed in linear algebra, up to the point that I'll even claim that these kinds of behaviors are actually linear algebra. Looks a bit strange at the moment, perhaps, but this is also linear algebra, and very important, translating between different bases that I gave some motivation in the previous lecture. And we will see that even anything that you can measure when a result is quantized or continuous comes out also from linear algebra. So we need to know linear algebra well in order to proceed. So I'll spend the last part of this lecture and perhaps the beginning of the next lecture on reminding us some of the properties of linear algebra. Okay, so Ehrenfest theorem. So Ehrenfest was actually a Jewish-Dutch physicist, a bit older than actually the same age as Schrödinger, a bit older than other participants in discovering quantum mechanics, like Heisenberg and Pauli, which we will run into in the following lectures. Actually, his main interest was not in quantum mechanics. That's the only contribution that we are aware of in quantum mechanics. He was someone who thought long and hard about statistical mechanics, thermodynamics, and as the tradition of physicists who contributed to the development of quantum mechanics, he committed suicide at some point of his life. Well, you know that Boltzmann did that.
Yeah, right.
So apparently this is a very depressing subject. Okay, so what is Ehrenfest's theorem? It's basically stating that Newton's law, F equal NA, is fulfilled for the averages of these operators in quantum mechanics. So I hope that you can convince yourself that that is NA. Not sure?
Why not? It's NA.
So, no?
Yeah.
Okay, so answer it.
Okay.
Otherwise, I can talk to an empty room.
As long as the mass is conserved, right? In time.
As long as mass is non-dependent on time, which, to the best of our knowledge, this is the situation. Okay, so since we don't have an operator for F, but we do have an operator for V, we defined that in the previous lecture. So let me write it the following. Okay, so the contribution of Ehrenfest to this statement is do the averages and it will be correct for quantum mechanics. Okay, let's see. How do you prove it? And let me, for for simplicity, although there's no problem in expanding it for py, pz, I'll keep myself to px. Why? Because that's the definition of average px.
Can I ask a question?
Yes, just please, with whom am I speaking?
Ben, why did dx have a vector?
As I discussed in the previous lecture, we could be working in more than one dimension.
Yes, but if we are in one dimension, as you say, we can raise them, right?
Yeah, if it's a one-dimensional system, so dx is dx.
Yes, okay, thank you.
If it confuses you, it has... The only thing is that I'm using Gauss's theorem further on, and if I'm defining a surface in one dimension, surface is a point, so just for that reason, but it really doesn't matter here. Okay. This depends on t. This depends on t. This doesn't depend on t. Not that it matters partial or... Okay, just a derivative of a multiplication, performs the derivative on the first, performs the derivative on the second. Order here is not important. Okay. So, I see that I have here a derivative of psi according to time. What do I know about the derivative of psi according to time? The Schrödinger equation. And we will use that connection. If I'm just writing down the Schrödinger equation, I just wrote down Schrödinger equation divided by I h bar. So I take these guys according to the definition and install them here. Okay, everyone has it. I can erase. Okay. So it might look long. All that I did is wrote the Schrödinger equation for the psi complex conjugate and the psi dot t. Just copied it and pasted it. So I got something long. Okay, now let's try to look into what's written here and simplify it. Okay, I want to remind you some math that you probably know, but perhaps you forgot. Let's say I have two functions f and g. Any functions are continuous and well behaved, but any functions. And let's say I have the following integral. Okay, why am I talking about it? You immediately see that it somehow reminds us what's written here. Why is that true? Just perform divergence and you'll see that you're going back to what's written above. Now I'll use Gauss instead of the integral over volume. I'll go to an integral over a surface and get here okay, so why did I bore you with this whole exercise? Let's check what's going on here. Here we have two functions that we can identify. Somewhere I got the plus wrong. This is a minus check. So if I identify this guy as G, I have exactly what's written here. Okay? Guys at home, okay? Anyone alive there?
Yes, yes, okay.
So, instead of this, I can write this. Now, we are dealing with a wave function. Wave function have to be normalized to 1. If it has to be normalized to 1 at the infinity, at the surface at infinity, it goes to 0. No other way. Not only that the wave function has to go to 0, also its derivative has to go to 0. And after that configuration, basically, I can write here so try to make last use of this. Why? Because the integral over volume becomes integral over the surface at infinity, and at infinity this guy and this guy must go to 0. Again, because a wave function is a square is probability, and if it doesn't go to 0, you'll have a divergent probability. Can't be. So we shortened our long and cumbersome algebra into only this part. Okay, let's see what we can do with this part. Why? Let's perform this guy. Okay? Psi dou to dou x of v is written here. On the other hand, psi dagger times sorry, psi complex conjugate. I haven't yet defined what is a dagger. Times v times psi is exactly this guy, falls off. And this is exactly how we perform the average of the derivative of v, which is a force. Ehrenfest's theorem proved.
I think that's true, not here, because you are doing partial derivatives with x, and we are only dealing things on the x direction.
So, since we did it, you are right mathematically. What do I mean? You are right that here I should have written and you're completely right. I just already expanded it to see this guy. If I would have done here instead of px p vector, we would have here a grad and we would have exactly. So if you don't believe me, go back and do the calculation for py pz.
You can only index the pi
Right, and
with
then
tensorial notation.
no, but strictly speaking, you're completely right. Can ask me. Okay, questions at home? Good. For end of first topic for today. So let's. Okay, stationary states is the headline that we give to the situation where the potential does not depend on time. In general, as I said in the previous lecture, the potential could be a function of x and t. And as I emphasized in the previous lecture, a lot of potentials, like an electromagnetic wave, does have a dependence on t. So we can't just say it's not relevant. But life becomes much simpler if we have a stationary potential, meaning depending only on x and not on t. Why is that? Because then solving the Schrödinger equation becomes easier. So, I'm rewriting the Schrödinger equation. And in this case, I can rewrite psi as a multiplication of two terms. So psi in general depends on x and t. F. I'm writing it as a function that depends on t times a function that depends on x. Okay, let's just replace psi everywhere with this definition. Okay, the only thing I used, this is f of t, of course, that in the derivative of t on the left-hand side doesn't have any influence on psi x, and the derivative of x that appears here doesn't have any influence on ft. Okay, so as usual, we'll just divide by psi and f.
There's a minus missing, right?
Let's see if no.
It's good.
But always check me, I have a tendency to lose minuses. As the old joke about Teret that was said in a seminar, and someone who gave the lecture said, well, I got a minus and made a mistake on the way, so Teret said to him, well, you made an odd number of mistakes along the way. Okay, so you should be familiar from any course that you took on differential equations that in this situation where I have a function that depends on one on the time here and on x here, we can assume that it's equal a constant. And at the moment, I'm calling it E. It will be energy, but at the moment, it's just a constant. I didn't prove that it's energy. We'll see it in a couple of minutes.
But it has unit of energy.
Yeah, but... And then we can solve the two equations that are equal to a constant. So the first one, let's write it already in an easier form. Just copied and multiplied by ft. And could someone give me the answer?
E minus E elevated to minus E I or E divided T. No, per T and divided H.
Right? If you're not convinced, perform a derivative. All the derivative will give you is minus IE divided by H bar. Minus I times I is 1. So H bar is cancelled and you have E on both sides. Right, so the form of Ft is a very simple form under these conditions. What is the solution to the right-hand side? Well, it depends on the potential. Can't answer, it's unique for any case. Square well, a one-dimensional square well doesn't look like the solution of a hydrogen atom. I don't know, but in general, it will be something that depends on E, must depend on E, and I'll write it down as and the general solution is okay. So the whole dependence on time appears as an exponent, as a phase. And we have here some dependence on x, which depends on the problems that you are trying to solve. A lot of times, the mathematical complication of solving the problem is in here. But once you have a stationary potential, doesn't matter if it's a square well, a harmonic potential, hydrogen atom, for all these problems, the time part is simple because these potentials don't depend on time. Okay. can we say about this type of solution? We can say a few very general things. What is the probability of finding a particle at point X at time t? Okay, we know it. Right? That's what we did the previous lecture.
The phase cancels out.
In this case, the phase cancels out. We have the probability depends only on the position, doesn't depend on time, doesn't change with time. So I can very easily tell you that if you had a picture of hydrogen atoms that has an electron orbiting the nucleus, it's rubbish. For the simple reason that the probability of finding this particle anywhere around the hydrogen atom doesn't depend on time. You can measure it today, tomorrow, in 200 years, still will have the same probability. Why? Because the potential doesn't depend on time. Then you can come and ask me, but we did something about angular momentum, so it goes around. Well, unfortunately, it won't be in this semester according to the new plan, but we'll understand what is the meaning of that statement. But if I go and measure the position of the electron, I have the same probability of finding it at any time. It doesn't have some oscillating time dependence, as you would expect from the naive picture of electron orbiting the nucleus. No, it's not. Okay, what else can we say? Okay, I'm writing here E, and as pointed out, it's units of energy, but how is it connected with the energy? Let's do the calculation. We know to calculate the average energy. We go and do our algorithm. I'm writing down the energy operator. Now, let's write the specific wave functions that we calculated for the stationary case. Pulled up psi of x because it doesn't depend on the time, so I don't have to write it within the derivative. Okay, I perform the derivative explicitly. And someone should tell me that I forgot to write. Oh, no, I will have written it down. Yes, sorry. Okay, I h bar times minus I divided by h bar. And the only thing that remains is E. And E is a constant. I can pull it.
And that's 1.
This is 1, and I times h bar times minus I is 1, divided by h bar is still 1. So the only thing that remains is the E, and this is equal 1 by definition. So the average energy is this constant E, that's why I wrote it as E. That's the state, and it doesn't change with time. No surprise here. If you have a stationary potential, a constant potential, the energy of a particle in classical mechanics doesn't change, right? So that's another demonstration of a case where the average quantity of the operator gives you what you expect from classical physics. Actually, the statement here is stronger. Let me do the following things that for you in your notebook is a bit more complicated, but let me go and look what is a power of it. Let's not be so general, let's write E squared. Okay. We know how to do it. The only thing that I have to do here is square it. If I square it, the only thing that changes here, again, it's squared. So this is squared and this is squared. And I end up with E squared here. We do it to the power of 3, 4, whatever. Power of n. So I'll give you a couple of minutes to just write it down.
The E before the integral, B to B double 2. No.
Right. Thanks.
Yes. Thank you.
So it's nice to see that Ben is alive and following. So, okay, think that, let's wait another minute. Okay, it looks as a trivial statement, but actually it's an extremely strong statement. Why? What is the variance of the energy here? Let's remind ourselves what is variance. I'll use
To 0.
no variance. If you'll check for any higher moments, you can reconstruct the probability, and the probability in this case would be a delta function. Just you will always measure the energy for a stationary state. Although a lot of quantities in quantum mechanics are probabilistic, for a stationary potential, the energy of the system is definitely conserved. That actually came as a surprise to Bohr. In 1924, before quantum mechanics was completely formulated, he tried to argue that in quantum mechanics, as position is probabilistic, energy also could be probabilistic. One of the things I think that it's correct, but you can check me at home. One of the things was the cases of some radioactive decay where energy disappeared, and one of the explanations was it's probabilistic. Pauli insisted, no, we are missing a particle, that's the neutrino, and energy is exactly conserved. Here is a statement. Here is the proof.
So the variance of E is 0?
Not only is it the variance is 0, this is something that I'm not sure that all of you have done in when they studied probability, but if you can write, if the variance is 0 and you can write all other moments, and basically we have shown that e to the power of n is e to the power of n. So then you can say that not only the variance is 0, any higher order is 0, and therefore, if you want to write down the probability function, it's a delta function. Not sure all of you can actually prove it, but that's the conclusion.
Thank you.
So for a stationary state, there's no probability finding E. You know what it is.
But in order to perform a measurement, you need to add energy to the system. The system can vary the energy.
Okay. As you noted here, I'm only asking about what I'm doing here is assuming that you have only a stationary potential.
Right.
Okay. In this situation, energy is conserved. If you measure by sending a photon, no.
Then
Even on a classical level, the potential that a photon induces is a time dependent, so electromagnetic wave.
Right.
So everything that I said here, not correct. Okay. Does it mean that I can prepare a quantum function only at a given energy? Or I'll be more exact, only for one solution of this equation. And here we actually go into the magic of quantum mechanics magic with parentheses. This is something that quantum mechanics is very different from our everyday intuition. The answer is no. And we will need the language of linear algebra to really understand what we're doing here. So I'll just illustrate the idea, will not prove it here, and will return with the full glory of a mathematical proof after we'll refresh our understanding of linear algebra. So I have the following equation. H is a minus H bar square over 2n. To write it explicitly. Important thing, only a stationary thing. That's the spatial part that we have written. And if I want to remind myself, I'll write here E. Okay. Because a lot of time in quantum mechanics is spent on solving this equation, people tend to call it the Schrödinger equation. It's not the full Schrödinger equation, it's a stationary Schrödinger equation. Okay. Does it have solutions for any value of E? Depends. Depends on the problem. For a free particle, it has a continuum of solutions above E equals 0. For a, let's say, a particle in a box, no. It has a discrete set of solutions. For the hydrogen atom, depends. Below E equals 0, the electron is bounded to the nucleus and it has discrete solutions. Above, that's ionizing the atom. It has a continuum. So it depends on the problem. I can't give a general answer for what values of E you have a solution. It depends on V. Let's say I have one solution And I have a second solution. Can I say something general about the solution? The answer is yes. I can tell you and as long as this is a solution of the Schrödinger equation. Now, why is that true? The reason is that these two functions are orthogonal, whatever that means. But if I write down, let's say,
It's kind of like a vector in R2, right?
forget it's kind like, it is exactly a vector.
We're getting to the point that is the eigenvalues. Yeah.
Right. But in order to convince you that the x everywhere. Okay, this is just expanding what's written here. But these guys, we will see, must be equal 0, and these guys are 1, and therefore, so if I have two solutions, I can put a superposition. So the energy will be constant, but could be composed of two discrete energies. Okay, and hopefully, why is this statement correct? Because we will show that any solution of vectors of an operator must be orthogonal, and we'll see what it means, but this is a justification why we have to go and acquaint ourselves with linear algebra.
It must be a Hermitian operator, right?
Yeah, and why does it have to be a Hermitian
Because
operator?
it's an observable.
It's observable, it has to give you a real eigenvalue. I didn't define yet what is an eigenvalue, but for all these reasons, we need to. You have studied linear algebra, but, well, first of all, I'm not so sure that all of you remember all the details, and details here are very important.
Why that two less integrals is equal to 0?
Stay tuned. After the recess, we'll go through it, and I'll convince you that these two functions are orthogonal, and that's the meaning of an orthogonal. I didn't prove, but I'll prove it.
Thanks.
Okay, so let's stop now and reconvene in 15 minutes.
洗课，上午，明天上午确实有一节课，下午要去宜家。咖啡去了。看见画的这么有戏呢。有戏。是爱肉。
משתדל לשתות את זה בגלל המסה. ראיתי כל מיני דברים בקלוריות, אחי. אין הכל, לא, חלב זה יתרחב בקלוריות. כמה יש שזה לא בריא. חלב זה המשקה עם אחר בקלוריות. הנקטר הזה שכמו קניתי, זה המשקה השלישי בעולם שראיתי שיש לו כמות כזאת של קלוריות.
חשוב שזה
חלב זה כאילו...
אוקיי, אתה יכול לעשות משקה בעצמך.
בסדר, נו, אני מדבר איתך על מה שאתה קונה, אחי, לא על...
האמת שאתה, כאילו... השאלה אם קוטן 12% בשבילך זה כמה שנים.
וואו, אחי, עכשיו אני מבין. תגיד, אבל מה, הוא הכניס כאילו את פסאי במטריצה?
פסאי עצמה זה בעצמה וקטור.
כאילו... זה וקטור, כאילו פסאי, ויש לו פסאי 1, פסאי 2, פסאי 3, פסאי 4 נגיד,
יענו, איך מזמינים?
לא.
יש לו צעה בכל מקום. סכימה.
כן, סכימה של פאי.
אוקיי.
אני מוצא את עצמי. נו, אתה עושה פאי 1, פאי 2, פאי 3, פאי 4.
זה כן.
ואז
לא מטריצה
אתה
פיזית
עושה אופרטור, ואז אתה מקבל...
זה לא פיזית מטריצה כמו שאתה חושב שזה מטריצה.
אחי, למה לא?
זה
וקטור.
וקטור עמודה.
בסדר, אחי. זה וקטור עמודה.
זה לא מטריצה.
אם אתה תצייר...
זה וקטור עמודה, זה לא מטריצה.
לא שלך.
זה וקטור עמודה, זה לא מטריצה.
שמע, אחי...
לא וקטור עמודה זה היה מטריצה.
כן, אתה מבין. עם עמודה אחת ועבור שורות...
כן.
זהו, אז מה אתה רוצה? זה די מטריצה. בן, איפה הוא? בן! הוא כאן? בן, אתה כאן? וואלה. תתחיל להרים איתי על וקטור עמודה או וקטור עמודה? תגיד, עשית את השיעור הבית בקוונטים?
כן.
בשאלות האחרונות יש שם משהו עם אוקסיג'ן
נכון?
רצה להסביר את הקוונטיזציה של פעם כמו שהיינו עושים במודרני.
כן, זה מאוד מודרני. השלב הזה מודרני.
כן, זהו.
זה לא הולך בתוויר.
מה? מה קנית? מה? קנית, קיבלת. מה? מעמד פסיכי, כבר...
למה לא לוקח את המעמד?
מה אני צריכה לעמוד? הטאבלט עומד לבד.
כן, אני אמרתי את זה כמו ראשון, שלא יכול לקחת מעמד, ואז אני כזה, יש לי מעמד.
אבל יש שם גם...
איך פותחים את זה?
ואם לאן אני אלך להדליק את זה?
איך פותחים את זה? אני לא יודע. שברתי לך מגלית.
לא, לא. לא תחבר.
אין, סבבה. עושה קונטיזציית בוער, כמו שהיינו עושים במודרני.
בשלב עשיתי פשוט כתבתי את התנאי, כי לא היה לי כוח לכתוב את כל הדברים שנכנסים.
אני מתחילה לפחד, אל תדעו לי.
המעמד מגניב, אבל הוא קצת קשה לפילוג. זה הכיס.
נראה שאני חושבת, רבית, אגב, אני אצליח. אבל אין אף אחד
מה הצחקת את זה שלך? במה?
כן. את מה אתה רוצה לראות?
הבנתי איך הולכים. אבל קראו לו, למה היית בציר? אני מבקש להמשיך בציר.
אוי, שטוב כבר, שטוב.
זה הבד.
הוא נוח לך, נוח.
ואת יכולה לחבר אותו ל... למה צריכה בעצם?
בעצם?
יש לו בלוטות?
וואו.
וואו. זה סקסי.
זה מדהים שזה של בר אילן.
נכון.
מה מגניב?
בר אילן יוניברס.
לכל דבר שמים את החרא הזה.
נכון, אבל
אוניברסיטת בר אילן.
היה לי גם בקבוק ואז באתי מבחן במכניקה.
יש לי עדיין תיק.
בר אילן?
היה מתנות של השבוע, ולא קיבלנו את הסכנות של השבוע.
אני זוכרת.
כן, כן, זוכרת?
פתאום כזה בדיוק.
הוא בחוץ.
Okay, so what we are doing now is mathematics, linear algebra. So whoever feels himself as an expert and knows everything, that's fine, but I'll start in the beginning. Of course, I assume that you have already heard it, so I'm going very fast through everything, but just so all of us will be sure that we have the language to speak about quantum mechanics. Okay, so it's linear algebra. And first part is we are dealing with finite spaces. Why finite spaces? Until now, all the wave functions that we wrote are infinite spaces, actually, but it's simpler in finite spaces, and it's nevertheless relevant also for quantum mechanics. Let's say the smallest space that is relevant is just a space of 2, which is spin. We'll acquaint ourselves with it, but at the moment we're completely general. The only thing that we assume is that we have a finite space. Okay, so a vector is a finite number of elements arranged in a vector. The only thing I have to know about the elements is that they are a complex number. So ui is a complex number. And n is a dimensionality. And so we'll feel ourselves special. We're doing quantum mechanics, not general linear algebra. So instead of writing a vector in this way, I'll use the Dirac notation, and this is a vector.
UI is the vector, the complex vector of U? Or?
No. UI is the ith element in the vector. It's a complex number. I can have one complex number, then it's really a scalar. I could have 2, I could have n. At the moment, I can't have infinite.
And we assume that it's complex because the wave function is complex?
That's the field on which it's defined, but at the end of we're not learning linear algebra just to learn linear algebra. We'll use it in quantum mechanics, And in quantum mechanics, we need complex numbers.
Okay, thanks.
So let's assume I have two vectors, u and v. How do I perform addition? I'll write specifically u1 till un plus v1 that is the property of addition. Scalar, which could be complex, of course, times u1 multiplication of two vectors. Actually, here I have two different ways to perform multiplication. A scalar product.
Addition of those not need between you 2 and V2 with the plus sign you don't need.
Here?
No, between U2 and V2.
Right, correct. Okay, what is important to note here is that since we're dealing with complex numbers, when I write a vector to the left, and just generally from here on, if I'm writing the vector with the great symbol to the right, it's a column. If I'm writing it to the right, to the left, then it's a row and complex conjugate. It's extremely important. For the same way that when we did integrals, always one of the wave function was complex conjugate. Okay, so you just multiply each component of the vector with the equivalent component in the second vector, and remember to use complex conjugate on the left. The result of this is, of course, a scalar. That's why it's a scalar product. We won't need it in the first semester of quantum mechanics, but it may appear in the second part, and nowadays is very useful since entanglement and things like that coming to. There is also an outer product of both vectors. Someone knows what is the result of an outer product? A matrix. But as I said in the first semester, we don't need it. We need only a scalar product. Okay, so what do we know about scalar products? And the whole list is basically trivial. We know I could give it as a home assignment because there's nothing really new in it. So, okay, if I flip the sides, it's the same multiplication, but in this case, V1 would be the complex conjugate and not U1. Let's say V is a combination of two vectors, each one of them multiplied by some scalar A and B. Remember, the scalar could be also a complex number. Complex number is a scalar. By the definitions, you don't believe, write down the form of this and you'll get it immediately. That's the norm of the function. Why is it important to us? Because of normalization. So, this is also sometimes defined as the norm.
We need to take the square root, right?
Right, so right. Two vectors are defined as orthogonal to each other if and only if U times V scalar multiplication is equal to 0. Let's say I have a set of vectors. Here U1 is not the first term of the vector, it's the vector U1 that has n terms. named an orthogonal set if meaning any two vectors in the set are orthogonal between them. Orthonormal if this multiplication is 1 if they are equal, 0 if they are not equal. Now you can see that it's no problem to turn any orthogonal set into an orthonormal set if you just divide every vector by its norms, which is known in quantum mechanics as normalizing the wave function. Now, as I say, I'm not proving here anything. I assume that you've heard it somewhere. It's just a refresher. So, if I have vectors of dimension n, the largest orthogonal or orthonormal set that I can build is of size n. I can't build a larger set that will be orthogonal or orthonormal. And I'll stop writing them both because if I have one, I can always turn it into the other. And this set of size n is a basis. What does it mean that it's a basis? It means that if I have such a set, we call it, okay, so I have a set, so I, M and EI shows an orthonormal Y because it's nicer and easier to work with. Any vector in the space could be written as the sum of these bases. Okay, so let's ask a question. If I have a space of dimension n, how many bases does it have?
And
How many bases or how many sets of?
How many sets of bases, distinct sets of bases does it have?
one. Infinite.
Infinite.
Right, I understand.
Let's think about a two-dimensional space. Okay, this is one basis, but now rotated in any angle, it's also a basis. So a basis is not unique. You can choose an infinite number of bases to describe a given space, let's say of size 2, which is exactly what's. So there's nothing unique about a basis. We will see that in quantum mechanics there is something unique about bases. But from the point of view of linear algebra, no. Whatever. Choose any base you want, all of them are kosher. Okay. How do I find these AIs? And this is a procedure that will return so many times that even if you forget the course, I hope you will remember the procedure.
We take one vector and then we do a normalization. We do orthogonalization for the other vectors. So within H of various vectors.
Okay, so let me define a bit more precisely what I do here. I have a base. It's orthonormal. That was supplied. Now someone comes with a vector u, and I want to write it in this base. So the procedure to go and do it is the following. I want to know what's, let's say, the L component in this basis, multiply it, scalarly multiply it by the vector, which means just by definition, this is why I like to work with an orthonormal basis, not only me, everyone. And let me put L. So all you have to do in order to know how to expand a vector in a certain basis, multiply it, do a scalar multiplication with each one of the basis vectors, and you'll get the amplitude in this base.
Inside of the triangles, it should be ui or epsilon I. Because you multiplied epsilon L with u.
Yeah, but u is defined here. You see?
Ah, okay. Yes, yes.
So I just write down the definition. That's right.
So,
Alright, thank you.
in a sense, you're projecting over an axis, right?
Exactly. Not in a sense, that's exactly what I'm doing. But since I didn't yet define what is a projection, we will define it in a moment, but scalar multiplication we define. So give me a vector, give me a basis, I have no problem to write this vector in this basis. Now I will rock your world. Hopefully not, hopefully you're aware of it. But I came and wrote this vector let's say right? That's how I started. Now I'm telling you, basically, I can write this vector in this way. The first component is the first projection, the second is the second. But these two are not necessarily equal. That's fine. When I write a vector, I implicitly assume that I know the bases. If I specified what is the basis, so everything is clear. If I come and write it down in this way that seemed naively okay, but now you're stopping in a moment and asking, well, sorry, what was the basis here? That's the natural basis of and U1 means U1 times this one, U2 times this one, UN times so we had implicitly we had an agreement when I wrote this basis that we're talking about. This vector we are talking about this basis. But there's nothing special about this basis. This is a representation in this base, and I could build an infinite number of bases, and all of them are okay. The most important thing that one has always to remember, the results of any physical calculation should not depend on what basis I project my vector on. Could be that in one base the calculation is much easier than in another base. There's no law of conservation of difficulty of performing the calculation, but the results, the physical observables that I calculated there, cannot depend on the basis. If it depends, you know that you made a mistake. So, if I'm not writing anything, so when I'm writing a vector this way, I'm not specifying the basis. This is a natural basis. If I'm writing the basis and writing the vector in this way, you know exactly what it means. It means again, there's nothing holy, nothing special, nothing outstanding about this basis. We will see that for calculating physical quantities, there are preferred bases that have physical meaning, but it's not necessarily this base. So, to end, basically, writing down U at some bases is equivalent to writing the following thing. Which is actually what's written here. Just I explicitly define what are the AIs. Extremely, extremely useful. Because what we'll do in a moment, we'll move from one basis to other basis. Because all of them are equivalent, and I'll use whatever is convenient. You need an example, or all this is trivial? Good. Since we have a shorter semester, okay. Let's assume that we have a vector U defined in one basis, and we have another vector defined on the same basis. Of course, it's a different. Now, from what I said before, you expect that you do the scalar multiplication in the same way. Let me prove that this is correct. Complex conjugate, never forget it. Forget it, the result comes out wrong. Epsilon I is just some basis, nothing special about it, some general basis. So this is just writing down the definition. these days we always look how to pull out a delta function. As expected. Good, but as we have seen, not all the world is wave functions or vectors. We need operators. So we introduce an operator, and in this, what does an operator? Let's remind ourselves what did it do in quantum mechanics that we have already learned. We take a vector, we use the operator on it, and what do we get? Another vector. Same thing here, we take an operator, use it on a vector, and get another vector. So, in the most general terms, so we write an operator, works on a vector U. You see why Dirac notation is very convenient. I don't have to write matrices, vectors, it's much more compact. I didn't even show you that an operator yet is a matrix. But the general language, this is an operator. The only important thing is that it doesn't get you out of your original space. You add a vector with n components, you're still with a different vector, but still with n components. That's all I need to know about it. And now, again, all quantum mechanics is a theory of linear operators, so operators can do many strange things, but in quantum mechanics, any operator of interest is a linear operator. What does it mean? Multiplied by 2 each component of the vector, also the result of the operator is multiplied by 2. Of course, if I use an operator on a vector and I want to define this vector with a specific basis, as we have defined, from here, I know what the operator does to every component of the bases, I know what it does to any vector in this space. That's because it's a linear operator. Okay, for the mathematically inclined, I need also the identity operator, which tells me that you use it on a vector, it gives you the same vector. That's the identity. Okay, what else can we do with operators? We can combine them. So let's say I have operator A plus operator B, and not surprising. Now we'll get to the surprising results. So that's addition. What happens for multiplication? This is basically the definition. First, operate B on U, and then on whatever vector you got from it, and you get a vector here, use A on it. Not necessarily commutative. We'll go to the definition of a matrix, which we haven't yet proved, but you know that matrix multiplication is not equal. That is actually the mathematical reason why Heisenberg went to matrices to write down quantum mechanics, because he needed something where A times B is not equal to B times A. Okay. Are any two operators necessarily non-commutative? No. They are not necessarily commutative, but they could be.
For example, the identity commutes with everything.
Exactly. Okay, what else do I want here? The only thing that I'm missing here is if I can define, it's called the inverse. The inverse of an operator, it means that if I use the operator, then use the inverse of the operator on it, you're ending up with the same vector. It's not necessarily that it's easy to find the inverse. If any one of you remembers something from matrices, an inverse of a matrix could be a frustrating exercise to perform, but there is an algorithm to find it. So, by definition, the inverse times the operator itself is the identity operator. So, now let's connect it to a matrix. So let's assume I have some, now you know that each time that I'm discussing vectors, I should define on what basis I work. So let's assume I have some bases and I'm shortening from E of K to just K. Doesn't matter, I have some bases. Which is also normal. And I have some vector. All of this we have previously defined. What am I missing? I'm missing, in order to define the operator, I have to tell you what it is doing on each vector, basis vector.
Should be I or Ki?
This is U, this is I. K or it doesn't matter.
Okay.
It's easier for you to replace I with K, that's fine, but since it's a silent index, it doesn't make any difference. Okay, so I have to tell you what omega does on any K. What does it do? It moves you to another vector. And how does this other vector look? So again, sum over the basis vector. No point in changing now the basis. I'm working at a given basis. But what the operator does, takes you the basis vector k and gives you back some other vector. Here's the components, and here's a k reminds me that this is the result of using the operator on the kth vector, basis vector. Okay. Let's go back to this. And just so we will not confuse U and K here. That's what it gives you. Okay. I'll go into it explicitly a bit more in the next lecture, but can immediately see that this is a matrix.
Dimensions, I and L.
Right, 2 dimensions going from 1 to n, so that's a 2-dimensional. No, the matrix has 2. It's a matrix. Yeah. No, the dimension is n on n.
Yes, and then we count on two dimensions.
On 2 indexes.
On 2 indexes.
Not to confuse dimension versus size. So any operator is a matrix. To whomever it's not completely clear, we'll show it explicitly, I guess, in next. Okay. Now I want to define a very useful operator which you have actually talked about a few minutes ago. And I'm writing it down here, 1, because it's useful, very useful. 2nd, it's very neat in our new notation. Okay, so I have to write an operator, something that takes a vector and gives me another vector, right? So this specific operator that's its definition. Cute. And what does it do? It takes only the k component out of any vector you give it. Let's prove it. So I operate pk on a vector. let's write down explicitly the operator. These are scalars, can move them ahead. Magic delta. Gives you
we defined that K and I are orthonormal one to each other.
It's an orthonormal basis. Where did I write? K and I are the same bases. I'm just using two indexes to describe them. It's the same.
All right.
Okay, so it's just the K component of the vector U. And my final statement, and try to prove it. Oh, it's not so, should take 30 seconds of that. If I sum up all the projection operators of a basis, I end up with the same vector. Because I take one component plus the next one, plus the next one, plus the next one, and write down just as an exercise to prove to yourself the statement. It looks trivial. It's extremely helpful in all kinds of calculations. We'll see it in the next lecture. I think we'll stop here. And are there any questions at home? Here? Okay, so I'll see you next Wednesday. זה?
לא, את ה-UK עם ה-UK עצמו.
UK כן.
אחרון, הדבר הכי אחרון. אחרון. אחריו, המעבר הזה, כאילו...
יש לי דלתה K.
הדלתה בסדר, מה זה אומר ספציפית?
אז אם I פה צריך להיות שווה ל-K בשביל שהוא לא יתאפס, אז יש לי רק רכיב אחד שלא מתאפס, שזה K. שזה UK, וה-K פה היה לי מקודם.
וה-UK עם K, מה המשמעות שלו?
וקטור כפול אמפליטודה, שהוא עדיין וקטור.
בעיקרון מה שעשית זה להטיל את U על...
עכשיו, בסיום כל משחק עם אופרטורים, אתה חייב להגיע למצב שיש לך וקטור. אם אין לך משהו מהמבנה הזה, אתה יודע שטעית. אם קיבלת סקלר או קיבלת מטריצה, לא יכול להיות. כי אופרטור שפועל על וקטור נותן וקטור. הולך בטיול